transfer coefficient for heat exchanger. So I will write it as U A del T. Okay. Again, it will be UI AI for the inside and UO AO, O is outside, del T for outside. Okay. Now very important thing. Just remember this. These are resistances. Okay? These are resistances. And the resistance in that case is 1 HI AI plus R wall plus 1 H naught A naught. So this is called overall heat transfer coefficient. U is overall heat transfer coefficient. Overall. Okay. U is overall heat transfer coefficient of an heat exchanger. U is similarly, like if I input here for convection, it will be H1AI, HIAI, right? In place of H, I'm writing U. Overall heat transfer coefficient for heat exchanger is U, right? You have to remember this and understand this thing. This is the most important. Okay? Inside, heat transfer, overall heat transfer coefficient inside, area inside. This, area inside. Okay? The product of these two are always equal to the heat transfer coefficient outside and area outside. Okay? It does not mean that area has to be same or heat transfer coefficient has to be same, but their product is always same. Okay? This thing is equal to this thing, overall heat transfer coefficient. Because when you are buying a heat exchanger, you ask what is the overall heat transfer coefficient. Or when you are designing a heat exchanger, you have to mention, okay, in the characteristics, like this is the overall heat transfer coefficient of the heat exchanger. So this is overall. Okay. So inside is going to be equal to the overall. Outside is going to be equal to the overall. And the product of these are also going to be equal to each other. Okay. This is very important. Do you have any doubt? So product of UIAI is equal to U naught A naught. UI is not going to be equal to U naught unless AI is, what is AI, AO? AI is the area here inside. A naught is the area here outside. So in heat exchanger, we need an overall heat transfer coefficient. Okay. Just like H is a heat transfer coefficient for convection, right? For heat exchanger, we need overall, which is denoted by U. What is U? If you multiply U with the A, which is area, it's overall heat transfer coefficient. So it is going to be equal to all the resistances. Okay? In place of HI, I have just written UI. In place of H naught, I have written U naught. Right? This is for convection, and U is overall heat transfer for heat exchanger. We will do some numericals and you will understand. Okay. So the same derivation is written here for a double pipe heat exchanger, right? The resistance is this from chapter 3. Ln d naught divided by di 2 pi kn. Okay, and the overall total thermal resistance for a double pipe is again this: convection, then conduction, then convection. Right? This is from chapter 3. Area AI is inside, so we are using di. AO is area outside, so we are using DO. DO is diameter of the outside pipe. DI is the diameter of inside pipe. Okay. Then what happens? This is from chapter 1, right? Temperature difference divided by the resistance. This resistance we have been writing H1A, 1 divided by H1A, right? So in place of H, I am writing U. U is the overall heat transfer coefficient. Unit is what? Per meter square degree Kelvin. Okay. The important thing is, since it's an overall heat transfer of a heat exchanger, it does not matter if you are writing only UI or AI. It is going to be overall heat transfer. Okay. It's a steady. It's not transient. If you remember from chapter 3. Once we had calculated heat transfer rate inside or outside the window, it was same. Similarly, the product of UI, AI is going to be equal to U naught, A naught. Okay. U is called overall heat transfer coefficient. This equation 11.4 is very important. Okay, so you have to understand this. What is written here? 1 divided by UIAI. U is overall heat transfer coefficient, A is the area. Okay, so 1 divided by UIAI is equal to 1 divided by U naught A naught. Okay, so this thing 1 divided by UIAI is equal to 1 divided by H1AI plus R wall plus 1 divided by H naught A naught. Okay, we are just replacing the chapter 3 stuff with the heat exchanger. Okay, so just remember this equation 11.4. Okay, then you have fouling factor. So in heat exchanger as well, if you remember from chapter 3, we had some air resistance, if you remember, right? So fouling factor is when you use heat exchanger for a long time, you have some corrosion or some water deposit on the tubes and they decrease the heat transfer. Okay, so that is called fouling. So the performance of heat exchanger usually deteriorates. Deteriorates means decreases with time as a result of accumulation of deposit. Right? These are only pipes. So if you are using the heat exchanger for a long time, you can have some salt deposit, okay, or some other stuff. So the layer of deposit, so this kind of deposit inside the pipes, inside the tubes. The layer of deposit represent additional resistance, right? So they represent additional resistance. Okay, I will show you chapter 3 alongside. This was chapter 3, steady heat conduction, if you remember, right? And remember this stuff from chapter 3, right? Same stuff now we are introducing overall heat transfer by heat exchanger. Same analogy, same method. Okay, it's not difficult. Same convection, this is conduction, this is convection. And then if you remember, we studied this thermal contact resistance, right? So similarly to this, in heat exchanger, we have fouling factor. Okay, fouling factor is which decreases the heat transfer. It happens because of the accumulation of deposit. Fouling factor is denoted by RF. R is for resistance, F is for fouling factor. The net effect of these accumulations on heat transfer. Two common type of fouling, precipitation of solid deposit in a fluid on the heat transfer surface or corrosion. If you, of course, like if it's an iron and you are, the water is flowing for a long time, it can be corrosion as well. So whatever is corrosion or precipitation of solid, these things decreases the heat transfer. Okay, so these act as a resistance. Right? So when you are calculating total resistance, right? So you have to add this. This is fouling factor, RFI divided by the area. So you have to add this. This is also resistance. Okay. You add this if there is a corrosion, PPT, right? This is called PPT, precipitation. So you add the fouling factor inside the tube, outside the tube. Okay. Okay, let's do one example. 11.2. So this is a double pipe. Okay, we saw this. Double pipe shell and tube heat exchanger is constructed of a stainless steel. Thermal conductivity is given 15.1. Inner tube of inner diameter DI is given 1.5 centimeter. Outer diameter is D naught and it is 1.9 centimeter, and an outer shell of diameter 3.2 centimeter. The convection heat transfer coefficient is given to be 800 watt per meter. This is inside, HI, I is for inside. Inner surface of the tube HO, O is outside. Outside is 1200 on the outer surface. Fouling factor, there is a fouling factor, so we have to add the fouling factor when we are calculating the total resistance. Okay, fouling factor RFI, I is inside, is given, and outside fouling factor is also given. So this question has two parts. They are asking two things. First is the thermal resistance of the heat exchanger per unit length, total resistance. The second thing they are asking is overall heat transfer coefficient inside and outside. Okay, so the overall heat transfer coefficient UI is inside, UO is outside, based on the inner and outer areas of the tube respectively. Okay, so let's see. Corrosion or repeating, which is called causing resistance. So this is called fouling factor inside. This is a type of resistance. RF, fouling factor resistance inside. I is for inside. Then there is a tube out. It's a double pipe, right? So they are pouring cold. TC, temperature cold. And this is out. TC cold. Okay, this is out. You are inserting TH, okay, hot water, and TH is coming from here. This is the direction of your hot water. This is the direction of your cold water. It's counter. Alright. The information is given. A part is asking total thermal resistance A part, and this is your B part. Understand? So for total thermal resistance for this question, we have to add the resistances, right? So A part is this total thermal resistance. HI is given in your question 800. Okay. AI is not given. AI we can calculate because diameter is given. Right. R wall is conduction. Right. In the cylinder. So this we can also calculate. H naught. H naught not. HO. Okay. HO is also given 1200. AO we can calculate. It's area. Area we can calculate, we have the diameters. So first we will start with calculating area. Okay, this one. This is your inside. DI is given, HI is given, RFI is given. We don't have area. So first we calculate area. DI. Okay. DI is for the cylinder. Once you have the area, you have the areas, right? HI and H naught is given. Okay, so the fouling factor is given. We have to add the fouling factor because fouling factor is also a type of a resistance, right? Fouling factor is also a resistance. So we add the fouling factor when we are calculating the total resistance, right? Fouling factor is given inside as well as outside. So this is inside, right? The heat transfer inside the water is by convection. In this is a wall, very thin wall by conduction. And then there is also a fouling factor, a resistance. So we add that. Then we come outside, right? This is also again convection. So this is our wall. Our wall in this case is a cylinder. So I'm going to write it as then 2 pi KL. Okay. This is the wall. Then you come on the second tube. Second tube again you have a fouling factor and then the heat transfer by convection. Any doubt until here? You understand the question, right? There is a double pipe heat exchanger. Cold fluid is giving. Cold fluid is inserting from here and then it is coming out. How is it coming out when it's between, there is a pipe? It's flowing over the pipe. Okay, it's flowing over the pipe. The hot fluid you are inserting from here and is getting out from here. Hot liquid will have high temperature here. It will transfer heat, right, to the cold fluid and then it will get out from this side. Okay, these pipes are very old. They have some corrosion, okay, or some PPT deposited inside the tube as well outside the tube. So those are called resistance fouling factor. RFI is for the inside, RFO is for the inside. So you have to add this when you are calculating total thermal resistance. Okay, when you are calculating inside you add this, when you are calculating outside you add this. From chapter 3, if you remember, if I open this thing, okay, if I rotate this thing, this is like this, right? So convection between the water, then this layer here is convection, and then again here convection from chapter 3. So convection you have I, you have calculated AI. Okay, AI you have calculated your pi. This is given. This is given. If this is not given, you assume 1 meter. So you input all of this, and you get.
The R total formula will be like this always, or we can sometimes
So
have zero.
if it's a cylinder, the R ball is going to be this from chapter 3. Resistance for cylinder. Right? If it's a plain ball, if you remember from chapter 3, it changes to this L divided by K. Otherwise, yes, the formula is going to be this for total thermal resistance. This was your question, right?
Yeah, and sometimes it have to be only zero, right? We can cut it out from the formula.
What?
From the problem. Maybe sometimes we can cut it out from the formula when it go to zero or don't have like
formula goes to 0.
The value is zero.
If value is 0, yeah, but value will not be 0 in your event.
Oh.
So it's not going to be 0. There will be some values here. So this is very important equation, right? Overall heat transfer coefficient inside, area inside, overall heat transfer coefficient for heat exchanger outside, area outside is equal to the resistance, and the total resistance in heat exchanger is this. If there is a fouling factor, you add fouling factor here. If there is a fouling factor outside, you add fouling factor outside. This R wall depends. This R wall, if it's a cylinder, it's going to be this. If it's a plain wall, it's going to be different. Right? This is from chapter 3. So B part is asking the overall heat transfer coefficient Ui and U naught. So as you can see, Ui, AI is equal to R, U naught, A naught is equal to R. Okay, this R is actually R total. This R is R total. Right? I have AI, I have A naught, I have R naught from here. So I can calculate Ui. Right? This R is R total. This R is R total. Understand? So from here, Ui will be AI R total. U naught will be A naught R total. AI is 0.0471. R total is 0.4530.
สอบอะไรวะไม่มี
จำไม่ได้ว่ามันเป็นแฟนของมันรู้แค่ว่ามันจะเป็นเจ้ากลุ่มทำแต่ว่าเขายังสอบไม่ถึงก็เลยคิดว่าน่าจะเป็นแฟนนนไม่ก็ต้องตลาด
โอเคเพื่อนไม่จ่าย
Second part is asking overall heat transfer coefficient, which is called U. Okay. From this you can see these are equal to R total. This R total is equal to this. So this we have already calculated, right? So from here we can say this is equal to R total. Ui will be this. Just input all the values for U naught as well. This will only change. Ai, E naught. In your A4 sheet, in your exam that you are bringing, write this formula so you can understand it. Okay. So this is your example 2. Okay, simple. So, analysis of heat exchanger. Next topic is okay. So, two different design tasks. If in your heat exchanger, temperature change in the fluid stream is given, mass flow is given, and you are need to decide or select a type of heat exchanger. Okay. The second case will be the outlet temperature of a heat exchanger is not given. Okay. Then how would you know the outside temperature? Okay, so there are actually two methods used in the analysis of heat exchanger. One is LMTD. LMTD means log mean temperature difference. Second is effectiveness NT. Two things. LMTD you use when the mass flow rate either is given or you can calculate. Okay, and you need to select a heat exchanger. Select means you need to understand the length of the heat exchanger, right? Effectiveness NTU method you use when the outlet temperature of a heat exchanger is not given. So there are two methods, okay? This method you use when the outlet means like this one. So let's say I have given you this type of heat exchanger and I am asking you the outlet temperature, outside temperature, right? Outside temperature is not given. So in that case, you will use effectiveness NTU method, this method, okay? So now you have lots of formulas, okay? Luckily, those formulas are given in a table, okay? So if I'm giving you a question, I will not provide the formula, so you have to write down the formula in your A4 size sheet. Okay. The analysis of heat exchanger can be greatly simplified by making the following assumptions, which are closely approximated in practice. Okay, this you can read. Okay. Then you have some derivations. All right. For mass flow rate, for heat transfer rate. Okay, and this is when there is a phase change. So in heat exchanger, sometimes you are boiling, right? There is a liquid, there is fluid, sometimes hot water, sometimes gas. So if you cool down the gas changes into liquid. So in heat exchanger, phase change is also happening. Okay? If you remember from chapter 1, phase change is there, then we use enthalpy, which is denoted by H. HFG is enthalpy. So I will write down all the formulas and log mean temperature. Okay, this is important. Log mean temperature difference. The temperature difference between the hot and cold fluid varies along the heat exchanger. It is convenient to have a mean temperature difference Tm for use in the relation. Okay. This is your parallel flow. Okay. So in parallel flow, if you see here, parallel flow, this flow, there is a temperature difference in this graph, right? This graph, there is a temperature difference, you denote it by del T. So this is what is written here. Here, this del T is the temperature difference between the streams, hot and cold. Okay, U is the overall heat transfer coefficient for heat exchanger. AS is the surface area. Okay, I will explain everything. So again, this is your parallel flow. Okay, why this type of graph? As I explained at the beginning of the chapter, this type of graph you understand, right? The hot and cold liquid temperature will increase, and hot liquid temperature will decrease, right? This we have understood. So if you take a smaller portion, okay, and then you calculate the heat transfer rate, del Q is in the smaller region, right? Del Q, and we are using del Q because it is changing, and we are using dt because this delta T is larger here, then it decreases here, right? Del T is the temperature difference between the hot liquid and the cold liquid, and it does not stay same throughout the heat exchanger. It is very high at the beginning, then lower and lowest, right? So this del T is changing throughout the heat exchanger. So that's why we are using D, differentiation, okay, T. And for a smaller amount, Q. Taking the differences, we get this, okay. Again, you don't have to go through the derivation, but you should understand what they are saying. Okay. So LMTD method, LMTD is log mean temperature difference. As an engineer, if you are selecting a heat exchanger or you are designing a heat exchanger, you want to know the length, area of the heat exchanger according to your suitability. Then you can use the LMTD method. Okay. So del Tm is the log mean temperature difference. Del TLM is defined as this. Okay, you cannot write del TLM as T hot minus T cold, right? Because this one is changing throughout the process. It's not same, right? So that's why you write it like this. Also, LMTD method you can use in parallel flow and counter flow only, and yes. So LMTD you use in parallel flow and counter flow only, and for multipass and cross flow heat exchanger we include an extra quantity. Okay. Let me write down. So you have two methods, okay? You have a heat exchanger, you want to calculate the mass flow rate, size of the heat exchanger, right? Then you use LMTD. Okay, we will do examples and then you will understand. LMTD stands for log mean temperature difference. If it's a parallel flow, you can use LMTD method in parallel flow, counter flow, multi-pass and cross flow. The formula for parallel flow and counter flow is different. Okay? Sorry, same, and for multi-pass and cross flow is different. I will write down the formula. So heat transfer rate, overall heat transfer coefficient, area, delta T, Lm is log mean. Okay. Alright. Why we are using delta T, Lm? Like I said, in the parallel flow and cross flow, the delta T does not stay same. It is changing throughout the process, right? I cannot write T1 minus T2. Like if it's a flow, if it's a pipe, T1, this is T2. I cannot write T1 minus T2, right? The temperature is changing throughout the pipe. Okay, so the formula for delta TLM is delta T1 minus delta T2. Inlet temperature, outlet temperature, right? Lin delta T1 delta T2. Okay, this is overall heat transfer coefficient. Area depend if it's a cylinder, if it's a wall. Okay. So this is for parallel flow and counter flow. For pass and cross flow, you have to add just one thing which is called correction factor. F. So your delta T
Not mean temperature difference. Not mean square.
CF is correction factor. Okay. This value of F we can calculate from grams. Okay, there are grams in the book. This is your multi-pass and cross flow. The log mean temperature difference relation developed earlier is limited to parallel flow and counter flow. Okay. To simplify the analysis of cross flow and multi-pass shell tube and heat exchanger, it is convenient to express the log mean temperature difference relation as this. F is correction factor. Delta T Lm is the log mean temperature for counter flow. Analysis of heat exchanger is done by two methods. First is LMTD, second is effectiveness NTU. LMTD you use that formula for parallel flow and counter flow. If it's a multi-pass and cross flow, you have to add F, which is correction factor. The value of F is given in the graph. So I will explain you how to check the value of F from the graph. Okay. Delta T is log mean temperature. Okay. The value of delta T Ln is delta T1 minus delta T2 divided by ln. Okay. But that is for parallel flow and counter flow. If it's a cross flow or multipass, you add one F only. Okay, that is the difference. Effectiveness NTU, I will explain later. Okay, let's take this example. Steam in the condenser of a power plant is to be condensed at a temperature. Whenever there is a steam and you are heating it or you are cooling it, there is high probability there is going to be a phase change. Okay, so steam in the condenser of a power plant is to be condensed at a temperature of 30 degrees Celsius with cooling water from a nearby lake, which enters the tube of the condenser at 1140 degrees Celsius and leave at 22 degrees Celsius. The surface of the tube is given 45 meters square. Overall heat transfer coefficient. Overall heat transfer coefficient is U. U is given 2100. Determine the mass flow rate of the cooling water needed and the rate of condensation of the steam. Can I move this? So delta TLM is delta T1 minus delta. So this condenser example is a counter flow. Okay, and now look very carefully. Delta T1 counter flow graph, if you remember, is like this. I explained at the beginning of the chapter. Right, the hot liquid, this is the counter flow. Right, the direction is reverse. Right, it's not parallel flow. So the hot water is highest here, and as it goes, the hot water temperature decreases. Okay, in here the cold water is here is at the lower temperature, and as it moves from here to here, the temperature increases of the cold water. Understand, right? This is clear? So cold water temperature here temperature is highest here, right? Highest here. Then I'm moving along this, the temperature decreases, right? The cold water is entering from this side. So the cold water temperature is very low here. And then as I move here, the temperature of the cold water is increasing. There is a heat transfer. So that's why the graph is like this. Your delta T1 is this, and your delta T2 is this. So what is delta T1? Delta T1 is hot in, cold out. Hot in, cold out. This is your delta T1. This is your delta T2. Delta T1 is hot in, cold out, cold out. Right? Delta T2 is H out. H is hot. Hot out, cold in. Hot out, cold in. Understand? Understand? Okay? So what is delta T1, delta T2? Understand? In here, this is delta T1. If you see this graph, or if you see here, hot water in, cold water out. Okay? This is your delta T2, cold water in, hot water out. We will always keep this as positive because this is higher temperature. Right? This one higher temperature. Okay? So this is T2, this is T1 in the counter flow. Okay? So this is your T1, delta T1, and this is delta T1, this is delta T2. T1, delta T1 is hot in this direction, cold out. Delta T2 is hot out, cold in. Delta T1 is hot in. In that diagram, hot is steam. In this condenser, hot is steam. Hot in, cold out. Cold out is this, cooling water. Cold out is 22. Delta T2 is hot out. Hot out is still 30 in the diagram. So it's 30. Cold in is 40 in the diagram. So we have delta T1, delta T2, we input here. And we will have log mean del T. Okay? So I input here, input this here, and delta T and LMTD. U is given 2100. Area is given 45 meters square. Delta TLM we just calculated 11.5. So heat transferred. constant pressure. M into C. T out minus T in, they are asking mass flow rate for the water only. So T out is water out, T in is water. Both are for water. Okay, so you can calculate mass flow rate from here. So this chapter is actually combination of all the chapters that you have studied. So you know all the formulas, but you just have to revise. For the steam, there is a phase change. Q we calculated. So this value is from table at the back of your book. Okay, CP for water, specific heat of water. This is from the book. Similarly, this value is also from at the back of your book. Heat of vaporization of water. I will just table A9. It's at the back of your book. This is also table A9. So the question was asking mass flow rate for the water and for the steam. Steam, like I'm saying, if you are cooling the steam, steam will change into liquid. There is a phase change. So you use the enthalpy. Okay, here. This value is from at the back of your book. Okay, if I'm giving you this in exam, of course I will provide the value. Alright. This is LFTT, this is a counter flow. In counter flow, from the graph, we know delta T1 is hot in, cold out, right? From the graph. Okay, hot in, cold out, and hot out, cold in from del T2. Okay, then just input very carefully all the values, looking at the your figure. Once you have the delta TLM, we know for the LMTD, Q is heat transfer, U is the overall heat transfer coefficient, A is the area, delta TLM we just calculated, this value is given, this value is given, this we calculated, you have this, right? Q is also equal to mass flow rate, specific heat, T out minus T in is for the water only, because they are asking mass flow rate for the water. So T out, T in just for the water, this 22 minus 40. Then they are asking mass flow rate of the steam. It's a steam, there is a phase change, you no longer can use this. If it was a water, second pipe also water, then you could have used this. But it's a steam, so you have to include the enthalpy. Okay, this one. Okay, this example is a little bit simpler and easy to understand. counter flow double pipe heat exchanger is to heat water from 20 to 80 degree at a rate of 1.2 kg per second. Heat is to be accomplished by geothermal water. Okay, so there is a geothermal water which is hot, and then there is a cold water. 160 degrees Celsius mass flow rate is given for both of the waters. The inner tube is thin walled and has a diameter of 1.5. Overall heat transfer coefficient is given. So overall heat transfer coefficient of the heat exchanger means U. U is given. Determine the length of the heat exchanger. So you use LMTD when they are asking length, when they are asking mass flow rate, right? And you use effectiveness, which we will do later, when they are asking you outlet temperatures. Okay. Any doubt in this question? Any confusion? Okay. Length of the heat exchanger. So we know heat exchanger is U E L. From this we can calculate the length, right? E will be equal to pi d L. We can calculate L. But we don't have any of these values. We don't have this value. We have this value. We don't have this value as well. Okay. So first length. So let's start with we know this is a counter flow again. In counter flow we know delta T1 is hot in, cold out, T2 is hot out, cold in. Okay. If you see this diagram, something is missing. You have for the hot water, for the cold water, you have TC in, right? Cold water inlet is 20 degree, right? Cold water outlet is 80 degree. You have these two values, but you don't have this value. You have this value. Hot in is 160 degree. You don't have this value. question they are asking length. Okay, if we have the area, this is a cylinder, area is pi dl, we can calculate L. Right? We don't have the area, right? So we start from here, we need del Tm. We don't have del Tm. Del Tm we know in counterflow is delta T1 minus delta T2, ln del T1 minus T2. We know del T1 is hot in, cold out, cold in. In the diagram, if you see, we don't have this temperature. We don't have this temperature, right? We don't have Q. We also don't have this. We cannot calculate A. We don't have this as well. We don't have this as well. We have this. This is given in the question 640. Okay. So first we have to find out this temperature. If we have this temperature, we can calculate delta TLM. Right? We don't have the outlet temperature for the hot water. Okay. So we can calculate this if we have the value of Q, M, Cp. This we are trying to calculate, right? For the hot water. Okay. T out minus T in. This is, let's say, is for cold, not for hot. We have this cold because we don't have the Q value as well. We can calculate the Q value from the cold water. Okay. Mass flow rate of the cold water is 1.2 from your question. Specific heat is not given, but at the back of your book, at this temperature, your specific heat is 4.18. T out of the cold water is 80. T in of the cold water is 20. You get the heat transfer 301 kilowatt. Just like chapter 3, your heat transfer rate stays the same. This is steady state, right? We can use the same Q for MCP out minus T2 for the geothermal. This value you have calculated from this. This stays the same because it's a steady state. Just like chapter 3, if you remember. The Q in chapter 3 we had like glass windows, right? You remember? The Q here was same in chapter 3. So just like that, this is going to be same here. So this is 301 for the geothermal water. Mass of geothermal water is 2 kg. Cp for the geothermal water is, from the back of your book, is 4.31. We don't know T out, we are trying to find T out. T in of geothermal water is 160. From here you can calculate T out. So your T out, hot out, is 125 degrees Celsius. So now we have this value. We have this value. We already had this value. We have calculated this value. So we can calculate it. We can calculate now delta T1, which is hot in minus cold out. Hot in is 160, cold out is 80. Right? Hot in. Hot out we have just calculated 125. 20, so get 105. Input this value in here. Then you get delta TLM. So I will directly write delta TLM will be 91.9 degrees Celsius. Okay. Now you have delta TLM. You have this value. You have this value. You have this value. This value is already given in the question. You can calculate A. At the end, we need to calculate the length. Length we can calculate from A. When we started the question, we did not have this. We did not have this. We all obviously don't have this. Okay. So we have calculated Q from here. Okay. Mass flow rate, specific heat, temperature out, temperature cold water. Okay. This Q is same for cold water stream and for the hot water stream because it's a steady state. There's no transient, just like chapter 3. Once you have the Q value, once you have the T2 value, T hot out value, you can input in here, right? Now you have this value, this value is already given in the question. You can calculate area. Once you have the area, Q we calculated from here, 301, right? Kilowatt. U is given in your question 640. Area we don't know. Delta TLM we have calculated 91.9. So I can calculate area from here, which is 5.12 meters square. Now we have the area. It's a cylindrical tube, right? Area pi dl. So we can calculate L. Diameter is 4.215 meters. So from here the L will be 109 meters. So LMTD you use in parallel flow, counter flow. When it's a parallel flow, counter flow, you use Q equals to UA del TLM. If it's a cross flow, multi-phase flow, you add F, which is correction factor. In here, in this example, it's a counter flow, we can simply use that equation, right? Q equals to UA. U is overall heat transfer coefficient, A is the area, delta T, Lm is the log mean temperature difference. It's a counter flow, delta TLM, delta T1 minus delta T2. From the graph, you remember the counter flow graph is like that delta T1 is hot in, cold out, and delta T2 will be hot out, cold in. Okay. Input all the values. This is maybe new to you, but this we have discussed in chapter 1 and 2. Q is equal to mass flow rate, specific heat, and then the temperature. Okay. This does not change. Okay. Since you are writing mass flow rate with the temperature difference, this is not going to be something like this, hot in, cold out. This is not what that is. This is heat transfer rate in that one pipe. Okay. M is mass flow rate, Cp is the specific heat for the water. Right? This is specific heat for the water, mass flow rate for the water. So the temperature difference is only going to be for water. Okay? T out of water, T in of water. You cannot write something like this. This is the temperature difference in the graph. Temperature difference. Okay? Maximum temperature difference. So delta T1 is hot in, cold out. This is not that. This is in the single pipe for the water. This is in the single pipe of the geothermal water. Okay? Yeah. This one or this one. And this is from the graph, delta T1. Maximum temperature difference. Hot in, cold out, hot out, hot. So now we have the cross flow. Okay, so you also have to look at the heat exchanger and you should be able to understand what type of heat exchanger is. This is not counter flow, right? This is not parallel flow. Okay, this is clearly shell and tube. Okay, this is shell and tube heat exchanger. Now shell. Shells are this. If you remember, this is one shell, this is two shell, four tube. 1, 2, 3, 4. 4 tube. So that's how you classify. Two shell and four tube heat exchanger is used to heat glycerine from 20 to 50 by hot water, which enters the thin wall 2 cm diameter tube 80 and leaves at 40. Total length of the tube in the heat exchanger is given 60. Convection heat transfer coefficient is given of the glycerine and of the water. Determine the rate of heat transfer in the heat exchanger. They are asking Q. Before any fouling, okay, we have to add the fouling in the B part, and A part is without the fouling. In the B part, you have to add the fouling. The fouling factor is 0.0006. Okay, and you have to calculate Q, rate of heat transfer. So you will use LMTD, right? But like I said, that simple thing, Q equals to UA delta TLM, you can only use for parallel flow and counter flow. Now you have a shell tube. So this you can use for parallel and counter. Now we have shell and tube. In shell and tube, if you remember, I told you we add F. So Q equals to UAF. Okay, delta T CF, correct? Sorry, counter flow. Okay, but for a shell and tube cross flow, this kind of cross flow. So UAF, F I will tell you now how to calculate in this system. The question is asking heat transfer rate before the fouling factor and after the fouling factor. So fouling, when we are calculating this, we just add the fouling factor. If you remember, right? From example 1. Okay. So let's calculate A part, which is Q equals to U A F delta T L M. So let's see first, we have to calculate this. We don't have this, right? Do we have this? U. No, we don't have U. So first, we don't have this, we don't have this, we have area at least. We have the area. They have given the diameter and length, so we can calculate the area. F we have to calculate always. Delta TLM also we have to calculate. So delta TLM is delta So the temperature everywhere is given. Okay, so you don't have to calculate temperatures anywhere. Just write this one very carefully. First draw the graph if you are confused, and then write down these very carefully. So this is 30, this is 20. From here I can write down delta T and M is going to be 24. 30 minus 20, then 30 divided by 20, 24.7 degrees Celsius. Okay. So now you have this. You still don't have this. You also don't have this. This you can calculate. So A is pi dl. A is pi diameter given. Diameter is 0.02 degree, 0.02 meter. 2 centimeter diameter. So diameter is given 0.02 meter. Length is 60. 60 meter length is given. So area I can calculate. So area is 3.77 meters square. So now I have this. I have this. I don't have this. F. I also don't have this. So F I can calculate. Or let's just calculate U first. U also we can calculate. U we can calculate from here. This is 1 divided by U. I can just say. Okay. These both are given. This is from here. U equals to. Okay. It is written thin walled. Thin walled. So we can assume this as 0. Thin walled. Okay. So you only have these two in here. Before fouling. Before fouling. After fouling, you have to add one fouling here, one fouling here. So this will become 1 divided by 160 plus 1 divided by 25 equals to 21.6. So now we have this value as well. We have to calculate this now. F. F is correction factor, and this we calculate from graphs. How? So this question, example 11.5 is asking heat transfer rate. This is the formula for the LMTT method. U is the overall heat transfer coefficient, A is the area, F is the correction factor. We will add F when it's not a counter flow. Now it's a shell tube. Shell and tube. So we have to include F. If it was only a counter flow, we would remove this. So we have to include F. How to calculate F now? F is given in these charts. Okay? And as you can see, you will include F only when there is a shell and tube and cross flow heat exchanger. this type of heat exchanger, this type of, or this type of. In our example, the heat exchanger looks like this, right? This one, not that one. Our exchanger is like this. The example that we are doing. We are doing this example, okay? So this is a shell and tube, 2 shell and 4 tube. So this graph, we will look at this graph and we have to calculate F, correction factor. So we need to calculate x-axis and these pink lines, and similarly like we did in chapter 4, if you remember Hessler chart. So in Hessler chart as well we were using the graphs, right? So similarly calculate the x-axis, calculate the pink line, and then track to y-axis, and y-axis is a correction factor. You use correction factor only for shell and tube and cross flow heat exchangers. Okay. So now what is x-axis? X-axis is denoted by capital P. Capital P is nothing, T2 minus T1, capital T1 minus small t1. Just look at the graph. Okay. This is small t2, this is small t1, this is capital T1, this is capital T2. Okay, just look at the graphs. So shell and tube, this is shell, this is shell, this is tube, this is tube, this is tube, this is tube. So 2 shell and 4 tube. Okay, so tube inlet is denoted by this, tube outlet is denoted by this. Small t is the tube and capital T are the shell. Okay. Now look at your case. In your case, small t is going to be this and this, right? And capital T is going to be this and this, right? So here, okay, small t2, small t1, capital T1, capital T2. From here, capital T1 is 20, capital T2 is 50, small t1 is 40, small t2 is 80. Just look at this graph and you have to calculate the correction factor from here. Correction factor is f-axis. So P you calculate from here. This pink line is called R. Same, T1 minus T2. Capital T is for shell. Shell inlet, shell outlet, and T2 minus T1, these are tube. Okay, so look at this graph, this diagram, and then look at your diagram what values are given for the small t and for the capital T. Okay, so now I will calculate F because it's not a counter flow. It's a 2 shell and 4 tube. So I need F. The question is asking to calculate heat transfer. I need F. So F I will calculate. From graph. X-axis of the graph is P, right? P, which is T2 minus T1 divided by T1, 40, 80, 20, the pink line is called R. R is T1 minus T2. Tell me the F and check if this is correct. T is T2 minus T1. What are T2? Small T2, small T1. This and this. So I have written the same, right? 40 minus t1 and minus t1, small minus small t1. So capital T1 is this, small t1 is this, right? So I have written the same. I have the x-axis. I will calculate the pink line. Pink line capital T1 minus T2, capital T2, and this. Just look at the graph, look at the your diagram, okay, and find out the. So what will be the f? You have the value of x-axis. You have the value of pink line. What will be the value of f? You have x-axis, you have the pink line. What will be the value of y-axis? Just look at the graph. F.
0.98.
0.91. Be exact. Nothing is going to be exact. It's a graph, but it's somewhere 0.91. Now we have the value of f. So we have all the values here. We can calculate q. U we calculated from here 2.16. Area we calculated here 3.77. F we just calculated 4.91. Delta TLM is this 24.7. So Q is so the difference between the A part and the B part is only fouling factor. Okay. So in the B part, I'm not going to solve the B part. In B part, you just have to add the fouling factor here. Okay. U is nothing but the sum of the total resistances. U is nothing but the sum of the total resistances. Right. This is very thin in the question. So this is 0. But you have to add a fouling factor. Fouling factor, yeah. So plus 0.006. I will just calculate the mu. For the B part, everything else will be the same, just here. This will only be the difference. So only U will change. Only this will change. This stays same, this stays same, this stays same. Only this will change for the B part. This will change because we have to add a fouling factor. And we add the fouling factor like this. Okay? Fouling factor is a type of a resistance. So we have to add a resistance. So we add a resistance here. There is a plus, there is a wall. This is 0 because this is the wall. Okay? So we just finished the LMTD method, right? This is where you use the LMTD method. So read these 5 points where you have to use the LMTD. Okay. Get some water.
เขาบอกว่า
ไปกินน้ำเลย
เขียนเพื่อนรู้แล้วเพื่อน
So when you read the question, and in the question you can identify one of these points, you use LMTD. LMTD has 2 formulas. One is for counter flow, parallel flow, and the second where you include capital F, which is correction factor, when it's a cross flow shell and tube, those exchangers. Okay. The last method of heat exchanger is when the outlet temperature is not given. When the outlet temperature, outside water or outside cold water is not given, then we use effectiveness NTU. Just like chapter 4, we were using some non-dimensionalized units, right? So we had non-dimensionalized temperature, we had non-dimensionalized time called tau when we were solving the Hessler charts. So similar to that, this is your chapter 3, and in chapter 4 we were using lot of non-dimensionalized. This is your chapter 4, if you remember, right? So these were non-dimensionalized. Tau, right? Tau is made up of time and length, and alpha is diffusivity. Then this axis was theta, non-dimensionalized temperature. Similarly, now in heat exchanger, when we are doing the effectiveness NTU method, we have to use some non-dimensionalized units. This method is based on dimensionless parameter called the heat transfer effectiveness. Okay, epsilon is equal to actual heat transfer rate divided by the maximum possible heat transfer rate. It's a non-dimensionalized unit. Actual heat transfer rate in a heat exchanger, same like we have discussed in the previous example. Capital C is MC. M is mass flow rate, C is specific heat. So M and C they have written as capital C. This is your derivation. This MC is capital C, this capital C. Okay. So Q is this, and when you are calculating Q max, so this delta max is different. Delta T max is the maximum difference in the temperature, which is going to be when there is a hot in and cold in. Epsilon is effectiveness, NTU. Heat transfer effectiveness. So epsilon is heat transfer effectiveness. I remove this.
ส่งอะไรวะต่างอะไรเอาที่เดิมเลยมึงยิ้มเหรอมึงคนนี้ยิ้มเหรอได้ถามไปเช็คเพื่อไปรีบใช้ไม่อยากได้
Most of the examples in most of the numericals, at the end it is written solve this by using the LMTD method or solve this by effectiveness NTU method. Effectiveness NTU transfer rate divided by maximum heat. This is MC T out. Okay, so in effectiveness NTU method you have to calculate this, which is called heat transfer effectiveness epsilon. This is heat transfer rate divided by the maximum heat transfer rate. When you are calculating this, you have to be very careful. These two look same, but of course there is a difference. Qmax in the denominator, this is in the numerator. So this one is Cc is again mass into specific heat, right? So this one you are calculating like C is for cold out, cold in, hot in, hot out. But when you are calculating maximum, heat transfer by maximum, hot in, cold in, because this is the maximum temperature difference in a heat exchanger, right? And you will also use the minimum specific heat. Okay. This one you will use the mass and specific heat of, if you are calculating for cold water, if you are calculating for hot water. This you will use minimum. If this is smaller than the hot water, you will use this here. And this is smaller than the cold water, you will use this here. And this will be the maximum difference. Okay. Whereas this will be, if you are calculating for cold water, cold out, cold in, hot water, hot in, hot out. Okay. So this is your heat transfer effectiveness. Then you have number. So NTU is number of transfer unit. Okay. And again you have lot. This is also a dimensionless unit. U is overall heat transfer coefficient. A is the area. C means C is again mass into specific heat. Okay. So that is also the minimum. Then you also have one more definition, which is capacity ratio, denoted by C, small c. Okay. So again you have a lot of non-dimensionalized units here. This I will write down all these three. And okay, don't freak out after looking this one. So when you are solving the NTU, when you are solving the heat exchanger problem with NTU method, you have two tables. Okay. If the question is asking you effectiveness epsilon, right? So you use these formulas based on what heat exchanger is given. If it's a double pipe, parallel flow, counter flow, if it's a shell and tube, if it's a cross flow, if it's all any heat exchanger. Okay. Depending on, so you have to write down all these formulas in your A4 size paper that you are bringing in the exam. So this is for when you have to calculate epsilon effectiveness. This table is for when you have to calculate NTU, number of transfer unit, for a double pipe, for a shell and tube, and for the cross flow. Of course, you also have graphs, but again graphs are not that accurate, so you use the equations. Okay, equation when you have to calculate epsilon, equation when you have to calculate NTU. Okay, we will do one example and then it will be more clear. Alright, if you can see here, like if the question is asking you to calculate NTU, right? So let's suppose I'm asking you to calculate NTU in a double pipe heat exchanger. So what is the formula? Minus lim 1 minus epsilon. What is epsilon? Epsilon, then you have to remember, or you write down in your epsilon is Q, actual heat transfer, divided by maximum possible heat transfer rate. Okay. Then C, small c. What is small c? Small c is capacity ratio. Okay. C min divided by C max. Okay. Only these two quantities. So this is actually very simple. NTU methods are very simple if you just know which formula to use. If they are asking you to calculate the effectiveness epsilon in a double pipe, let's say parallel flow, so you need only NTU in value of C. What is NTU? NTU is this. Okay, so let's do one example. Counter flow double pipe heat exchanger is to heat water from 20 to 80 degrees Celsius at a rate of this. Heating is to be accomplished by geothermal water. Mass flow rate is given. Inner tube is thin walled. Okay, thin walled. The R wall is 0. Has a diameter of 1.5. Overall heat transfer coefficient of the heat exchanger is 640. Using the effectiveness. So they have written you need to use the effectiveness NTU. Using the effectiveness NTU method, determine the length of the heat exchanger required to achieve the desired heating. Length. Provided U, right? So, and it's a counter flow double pipe. Counter flow double pipe, counter flow. Okay. So, and they are asking length, right? So, so you have two tables, right? Like I said, first table is for effectiveness coefficient, right? Epsilon. If you use this table, you can use this, of course. Counter flow double pipe, right? Then you will have epsilon. But the question is asking length, right? If you use this table, you will get NTU. Now NTU is equal to UA divided by C, area. Once you have the area, you can calculate the length. You understand why we are using the NTU table and not the effectiveness table? Because if you, so you have two tables. First table is this. If you use this double pipe counter flow, this equation, you will have epsilon, right? Anyway, you have to calculate NTU. NTU is not given in your question. The value of NTU is not given in your question. So you cannot use this table, right? You can use this table because this small c and epsilon you can calculate, right? So we will use this formula. In the table, this is a counter flow double pipe. Counter flow double pipe. So this formula I will use. Okay. counterflow heat exchanger. Okay. So in the question itself, this value is not given, this value is not given. But I know how to calculate. These are all non-dimensionalized units and they have their values. Epsilon is equal to this. Right? So I calculate the value of epsilon NC and then I input here and I will get the NTU. Okay? The question is asking length. NTU is also equal to area multiplied by something. So once we have the area, we can calculate. Okay, so effectiveness NTU method. First, what I'm writing here, you need to know these values, not dimensionalize it. First is epsilon. Okay. Then you have effectiveness NTU method. And then you can input and calculate. So first we will calculate epsilon. Epsilon from here is actual heat transfer rate divided by the maximum possible heat transfer rate. This is actual, this is maximum. I'm calculating actual. So Q actual is for water, right? So mass of the water is given in the question, Cp is given in the question. coefficient, right? Heat transfer, actual, maximum heat transfer. Actual for water is mass of the water, specific heat of the water, temperature of the water, only cold water, outside and inside. Outside and inside in the figure, cold water, 80 minus 20. Maximum is maximum temperature difference. So hot in and cold in have the maximum temperature. Hot in temperature and C min. C is the product of mass and specific heat. Okay. So you have to use minimum C. So first I will calculate the C for the hot water and cold water. Hot water, mass of hot water, specific heat of hot water, mass of cold water, specific heat of cold water. Then I have these. In these two, whichever is the minimum, I will use that. So this is the minimum. I will use this. When I am calculating this actual heat transfer. So maximum, for maximum I will use 5.02. T hot 160. T hot in and cold in is 20. Okay. From here I have Q max, which is 7028 kilowatt. Once I have this, I can calculate epsilon. So my epsilon is 301 divided by 702. Okay. So epsilon is Q max. Epsilon is 301.0702.8. Epsilon is 0.428. I am using this formula. I have epsilon, but I still don't have C. What is C? C is C minimum divided by C max. C minimum, C max. What is C minimum? This 5.02 divided by 8.62. So 5.02 divided by 8.62. It will be 0.582. Once I have the value of C, I have the value of epsilon, I just input here and I will get the value of NT. But the question is asking length. For length, okay, now from here, if I have the area, I can calculate length. I have the value of NTU, I have the value of U, I have the value of C minimum. So I can calculate A. Do you have any doubt in any step? I explain again. So this is a counter flow, double pipe, asking length. Okay. And they have said that you need to use effectiveness NTU only. In effectiveness NTU, you have non-dimensionalized 3 units: epsilon, small c, and NTU. Okay. Double, you go to the table and you see for the double pipe counter flow, you have this formula, right? In this formula, I still need epsilon and small c. Epsilon is actual heat transfer divided by maximum heat transfer. For actual heat transfer, you will use all the quantities of water only. So mass of water, specific heat of water, outside of water, inside of water. only. But when you are calculating maximum heat transfer, you will use C minimum. What is C? C is the product of mass and heat capacity. Okay. So for the cold water, M and C is this. Cold water, hot water is this. Out of these two, whichever is minimum, you use that when you are calculating Q max. So out of these two, minimum is this. So you input that here. Here as well you need to write down when you are calculating Q max the maximum temperature difference. Okay. So that is hot in and cold in. That is when the temperature difference is the highest. So you write down that here. Once you have Q and Q max, you have epsilon. Right? I need epsilon. I also don't have C. What is C? C is C minimum, C max. What is capital C? Capital C is nothing but product of mass and specific heat. C minimum is I have 5.02 and C maximum is 8.62. Maximum is from the hot water and minimum is for the cold water. I divide these, I get small c. Now I can solve this equation. Once I input everything here, I get the value of NTU 0.651. So NTU is equal to 0.651. NTU is also equal to U A C minimum. I have everything. I can calculate A from here, which is 0.65 C minimum divided by U. C minimum is this. U is given in your question, so you can calculate A. Once you have the A is equal to pi dl. They are asking length eventually, so you can calculate L. You just have to write down in your A4 size the equations. These. You have two tables for effectiveness.
Teacher, how do we know which one will be C min or C max?
C min, whichever value is lower. This value is lower, so this is C min.
So we have to find value C of two fluid.
So you have two fluids always, right? So calculate the C, let's say hot and cold. For the hot, you use mass of hot and specific heat of hot. Mass of cold, specific heat of cold. The result, whichever is minimum, is C minimum. Okay? If this was 5.02, then yeah, you will use this. Okay? Whichever is minimum. So minimum most of the time is going to be cold water. Examples are very important in this chapter. You start with 11.2 because 11.1 has an equation of convection which is from internal convection chapter which we have not studied. So you start from example 11.2 and solve until example 11.9 and also these questions. Okay. And next class is your last class, which is radiation heat transfer. Very simple, you don't have to go into detail again. So we will solve the assignment first in the next class and do the radiation chapter. Okay. If you have any doubt, please ask.